Hi guys, this is section 8.3 and we're on properties of inverse functions. Our goal today is we're going to examine situations and when the inverse is actually also a function, and we're going to use that inverse function theorem to determine if two functions are inverses of each other. So it's a way to check to see if they are inverses. Okay, here's a journal choice if that interests you. Let's talk about codes for a minute. And I think this is a good application of what inverses actually are. In chapter 5, and I don't actually think I had you do this part, but there was an example where you could, I think maybe we did talk about it a little bit, like encryption. Like if you are going to write in codes like to sell secret spy stuff to different governments or something. You obviously don't want to be caught, so we do these different encryption things. Well, obviously one's not going to be this easy because it would be very easy to figure out. But let's say that the code was 3x plus 11. And then each letter of the alphabet stood for a letter. Okay. For example, if A is 65, then maybe you'd say B is 66, C is 67. Okay. And then if you had a message, you could plug in 65 here. It'll be 3 times 65 plus 11 is 206, and then they would write 206 down, which 206 is nowhere on here. But if you saw the number 206, you would know that was letter A. Okay? And then we could figure out what B is by plugging 3 into this. Okay? So let's say that you are given this set of numbers, and you are trying to figure out what the heck it says. Okay? How do you do this? Well, you would have to take 212 equals 3x plus 11, and then backwards solve, minus 11, minus 11. So that'd be 201 equals 3x, divide by 3, and you get 67, okay? So we get 67 equals x, so I know this first letter is what, C? Okay. Now, I would have to do this process every single time. It would be so much nicer if I had a formula such as this that I could just plug into my calculator, look at the table, and get these number values very quickly so I didn't have to do the math every time. Okay? This undoing process, undoing this code that was already done, is the inverse function of f. So in question 13, you're going to use the inverse function to decode that above message, but it'd be easier if you found the rule for it. You could type it into your calculator and get the list of numbers instead of having to do it each time individually. Okay, and that's kind of what we're going to talk about today. So how can we get that rule? Okay, well, what you do is you still switch x and y and you solve for y. And the new function is the inverse or the undoing function. So we go back here and it was 3x plus 11. That's your original. So the inverse will be 3y plus 11 equals x, and it got to solve for y, minus 11, 3y is x minus 11, and make sure you divide the whole entire thing by 3, and you get x minus 11 over 3. That is the inverse, and you can write it like this, f inverse of x equals x minus 11 over 3. You could type that in your calculator, and then you could get all of those values that you're looking for and transfer them to letters very quickly. They are giving us the y now, and we can find the x. So it's a way to get around working backwards every time. Okay? Here is an example, 1/3 plus x over 12. I don't know what example this is from. Work with a partner to complete the following steps. One you should work with is 12x minus 4. The other should work with this. I'm just going to do them both right now, except we're not going to use a cast. We're going to do this by hand. Using the method described on the previous page, find the inverse of your function. So let's do f of x. F of x is 12x minus 4. Another way of writing that is y equals 12x minus 4. So I'm looking for f inverse. I'm going to switch x and y and solve for y. F inverse of x, this is what I'm going to do. X equals 12, y minus 4. Add 4, add 4. X plus 4 equals 12y. Divide both sides by 12, and I get, I'm going to space here, x plus 4 over 12 equals f inverse, or y. Okay? Another way of writing this, if you notice, I could write 1/3 plus x over 12. These are inverses. F of x is inverse is 1/3 plus x over 12. Let's see if the opposite is true. Is the inverse of f of x here going to be this 12x minus 4? Let's see what I have. Oh, I don't want to do that. Pretend that didn't happen. Okay, so I wish they called that g instead of f. But now I have y equals 1/3 plus x over 12. I'm looking for the inverse. So I'm going to switch x and y. X equals 1/3 plus y over 12. Okay, subtract 1/3. X minus 1/3 equals y over 12. Multiply both sides by 12, and when you do that, you need to do that with parentheses. 12x minus 4 equals y. And so they are inverses of each other, okay? So that's important to note, that they are inverses of each other. Now the last thing they want us to do here is find f of g of x and g of f of x. This is good practice to what we did yesterday. So let's look at f of g of x first. See, this is supposed to say g. This is the whole problem here. Alright, f of g of x. So f of 1/3 plus x over 12. Tells me to go to function f. I'm going to write it out here so you have it. Go to function f and plug this in. Well, f is 12 times x, which I now have to plug in this whole function, minus 4. Distribute here. 4 plus x minus 4. And the 4's cancel, and I get f of g of x equals x. Okay, let's try g of f of x now. That'll be g of 12x minus 4. Plug that into function g, and I get 1/3 plus 12x minus 4 all over 12. That's the same thing as 1/3 plus x minus 4 over 12, which is minus 1/3. The 1/3s cancel out, and I get x. So in this case, g of f of x equals x. So f of g of x equals x, and g of f of x equals x. Okay, let's talk about this. Does this even make sense? Of course it does. Because if this was my original function, the inverse undoes it. So basically I'm doing something to x when I plug it in, and then I'm undoing it. So what am I left with? I should just be left with x, whatever I plugged in to begin with. Okay? When you compose two functions, and this is what this inverse functions theorem says, when you compose them, do one followed by the other. If an inverse is doing something and then undoing it with the original, then you should be left with what you start with. So to check if an inverse is a function of each other, you can compose the two rules or relations or functions to see if you get what you started with. And there is the word and. You have to do it both ways. You have to check f of g of x and g of f of x, and you have to see if when that happens you get x for both. Okay? So let's try this example. If f of x is 2x plus 6 and g of x is 1/2 minus 6, are they inverses of each other? Well, let's check. First, let's do f of g of x. Okay, it's going to be f of 1/2 x minus 6. Go to function f, so it's 2 times, now I'm plugging in 1/2 x minus 6. Really be careful with your parentheses here. Plus 6. Distribute. X minus 12 plus 6. X minus 6. Okay? So f of g of x, I get x minus 6. So right away, I know they are not inverses of each other, because when I plug them in, I did not get x. Okay? Recall that an identity function is a function that maps each object in its domain onto itself. So y equals x is an identity function, because when I plug in x, I'm going to get the same thing back for y. Okay? Another way of saying the inverse function theorem is to say that the composite of two functions are inverses of each other and is the identity function. So we can say the multiplicative inverse of a number x is designated by x inverse. Similarly, when a function f has an inverse, you can just write f negative 1, which I already used that notation on the previous page. Okay, so here is the rule that you need to check. And that is how you can write, if you have a function and its inverse and you compose them with each other, you should get x, what you started with. Okay? This is another way of writing the f of g of x thing, but we're now using the function notation. So this rule that we just wrote down here is the exact same as this, except I would say that you're going to see this notation more commonly used than the other one. Okay? If you have an inverse and a regular function of each other, you compose them, you should get x both times. Okay, halving is an inverse for doubling. What is an inverse of squaring? Well, it should be what undoes squaring, square rooting, right? Okay, and here's another example. They would like us to find the inverse of h of x here. Well, the original function is y equals 4 times x plus 7 minus 3 all over 2. To find the inverse, we switch x and y and solve for y. So x is 4 times y plus 7 minus 3 all over 2. Okay, step 1 is to multiply both sides. Actually, I would probably clean this up first. This is optional. 4y plus 28 minus 3 over 2. I'm going to go up here. This is a little bit out of order here. 4y plus 25 over 2. Okay, now let's solve for y. First thing I'm going to do is multiply both sides by 2. 2x equals 4y plus 25. Subtract 25. 2x minus 25 equals 4y. And we divide both sides by 4. And we get h inverse, or y, equals 2x minus 25 all over 4. And there's my final. It's a little messy. You're probably going to need some space, loose leaf paper. Spread out your answers. Don't crowd yourself like I was crowded here. Okay? Thinking back to the nth powers and roots, if f of x is x to the n, and g of x is x to the 1 over n, and the domains of f and g are the set of non-negative real numbers. Notice non-negative real numbers means positive plus 0. Then they're inverses. So they're saying x to the n and x to the 1 over n are inverses, but only if you're talking about positive numbers and 0. Okay, why do we stipulate that? Why did we make that rule? Well, let's look at the graph here. If it is an even power and an odd power, you're going to have two different things that happen. First of all, if it was odd, we really wouldn't have that much of a problem. Y equals x to the 5th is going to look like this. Its inverse, when you reflect it, would look, I'm really bad at drawing this. Kind of like, I don't know, kind of going the other way maybe? I don't know, I'm really bad at drawing it. It would be okay. The problem that we really have are these even ones, okay? Y equals x to the 6th looks like this, and therefore its inverse would look like this. That's okay, that is its inverse, but this is a function, and its inverse here is a relation, because it does not pass the vertical line test. If I stipulate we're only talking about positives, and I get rid of this piece, okay, I would also end up getting rid of this piece, in which case they are both functions. Okay, so when you have something that would not pass that horizontal line test, so that the inverse would be a function, you could restrict your domain so that the inverse would be a function, because sometimes it is helpful to have a function for your inverse so that you can come up with a rule for it. Okay, so this is showing you why it is helpful to restrict the domain here so that the inverse would be a function. Okay, and that's all I have, and we will go over lots of examples on this when you get back to class.